In this example, we are going to calculate the weight of an object on the surface of a planet Mars and at the position well above the Martian surface. Suppose you are involved in the design of mission carrying humans to the surface of Mars, which has radius of 3.38 times 10 to the 6 meters, and the mass of Mars equals 6.42 times 10 to the 23 kilograms. The Earth weight of the Mars lander is, let's just write W equals 39,200 newtons. We want to calculate the weight Fg of the Mars lander and the acceleration due to the Mars gravity, G Mars, first, we want to do it at the surface of Mars. So, A, at the surface of Mars, and B, we want to have certain height, like a 6 times 10 to the 6 meters above the surface of the Mars. I'm going to call it an H. H equals meters above the surface of the Mars. So pretty much we have a situation, if we try to visualize, we have, let's suppose this is the Mars, and so here's the distance, the radius of the Mars, and we have mass of the Mars. First part of the problem, when we want to calculate the gravitational force at the surface of the Mars, and we want to find out the G of the Mars, and this is our lander, so mass of the lander, Mars lander. To find the gravitational force, we just are going to use the law of universal gravitation, that equals G times mass of the lander, mass of the Mars, I have it at capital, mass of the Mars, over the radius of the Mars squared. Now, we have everything, but we don't have the mass of the lander, but we have the weight of the lander, and we know that the weight of the lander on Earth, by the way, this is, we know it's on Earth. Okay, so weight on Earth equals mass of the lander times G on Earth, which we already know. So the mass of the lander will be the weight on the Earth of that lander over G on the Earth of the Earth, which is, let's plug in the numbers, 3.92 times 10 to the 4 newtons. I made this one in scientific notations. Divided the 9.80 accepted value, meters per second squared. When we use our calculator, we'll get a 4.00 times 10 to the 3 kilogram. Now that we know this value of the lander, we can plug it into our equation for gravitational force and do the calculations. So I can write F gravitational equals G is value of G is 6.67 times 10 to the negative 11 newtons times meter square over kilogram squared times, so we have the little mass of the lander, which is a 4.00 times 10 to the 3 kilograms, times the mass of the Mars, which we have 6.42 times 10 to the 23 kilograms, divided by the radius of the Mars, which is 3.38. Let me double check. Yes, times 10 to the 6 meters squared. So if we punch this into our calculator, we'll get the result 1.50 times 10 to the 4 newtons. Okay. Now to find the acceleration due to the gravity of Mars at its surface, so we will do gravity of Mars equals force of gravity divided by the mass. That equals 1.50 times 10 to the 4 newtons divided by 4 times 10 to the 3 kilograms, and we will get 3.75 meters per second square. Wow, this is a pretty small value, although it's more than on the moon, because the gravity on the moon is 6 times less than on the Earth. So it still will be easy to walk on the Mars. You might want to think like, okay, can we get the G from a G on the Mars from in a different way? Well, we absolutely can. We could use G little mass times mass of the Mars over I'm sorry, we don't have this little mass anymore. So we have the G mass of the Mars and then R of the Mars squared. And that, if you plug it in, let's see, 6.67 times 10 to the negative 11 newtons times meter square over kilogram squared, times 6.42 times 10 to the 23 kilograms divided by 3.38 times 10 to the 6 meters squared. This will give us the same value of 3.75 meters per second squared. Okay. Now the second part of the problem, it says to find the gravitational force at the height of 6 times 10 to the 6 meters. Now, if we do that, part B, in this case, our situation is this. So we have the Mars. Okay, so from here to here, we have the R of the Mars, and then up here we have the height that is given to us. So we want to find out what is the gravitational force right here, and the lander, suppose it's in here. Okay, it's in the process of landing mass. So we will do gravitational force at that distance equals, we could actually write G times mass of the Mars times mass of the lander divided by r of the Mars plus the height squared and calculate it. But I'm not going to do it. Instead, I am going to let you do it on your own and find the answer, and you should get the value of gravity at a certain height, at the height that is given to us, should be 1.95 times 10 to the 3 newtons. And gravity at that height, gravitational acceleration, equals 0.487 meters per second square. So this should be your answers. But you need to do the calculation. You do it. So if you look at the answers that you are supposed to get, you will see that the gravitational acceleration 3.75 on the surface and 0.487 on the at the certain height at 6 million meter above the surface are really greatly different from each other. So on the surface of Mars, gravity and the G, gravitational force and the G are roughly 40% as large as they are on the surface of the Earth. At the point in the orbit of Phobos, they're 13% as large as they are on the surface of Mars. Thanks for watching. Stay tuned for more.